You think your shaft's big enough? It's probably not. Stick with me and I'll walk you through the 5 biggest mistakes contractors and designers make when they plan MEP shafts in buildings. Before we get going, let's talk about what a mechanical or utility shaft actually is. A shaft is a vertical opening in a building that lets mechanical, plumbing, electrical, fire protection, and other systems run from floor to floor. On big commercial projects, these shafts turn into some of the tightest, most fought over spots in the whole building. The first challenge is just figuring out what the shaft is supposed to really look like, and the information is scattered all over the place. Architectural, structural, mechanical, plumbing, electrical, fire protection drawings, plus the BIM model. And here's the problem. They don't always match. The architects might show one shaft size, the mechanical engineer might show something different, the electrical engineer might need even more space than what's shown on any of the drawings. And I can almost guarantee you one thing, whatever's shown on the structural drawing is exactly what the concrete contractor is going to frame up and pour. So if that open is wrong, too small, or missing the support it needs, you're going to be living with that problem for the rest of the project. That's why PMs, foremen, superintendents, and coordinators need to start reviewing shafts really early. They need to check the drawings, check the model, verify slab openings, and make sure that what's being designed can actually be built. So let's dive into the 5 biggest mistakes contractors and designers make when they plan and install MEP shafts. Mistake number 5. Nobody plans for the shaft steel. On a lot of large commercial projects, the engineer will lay out the piping, the ductwork, and the conduit in the shaft in the model, but very little thought goes through what all this stuff is actually going to sit on or hang from. A lot of times the shaft steel isn't even shown at all. The design team may not have coordinated it with the structural drawings. They may not have calculated any of the weights. They may not have even calculated the insulation thickness or fully realized that the mechanical, plumbing, electrical, and the fire protection are all sharing the same space. And then construction starts. Now, somebody has to figure out, how much steel do we even need? Who's going to design it? Who's paying for it? Who's going to fabricate it? And who's going to install it? A lot of the specs push this onto the contractor through what they call delegated design. Miscellaneous metals rarely carries it in their scope, and the GC usually will just tell you it's yours. And all of a sudden you're chasing engineered drawings and stamped calcs that should have been talked about months ago. Now that steel has to be sized, loaded, and it's going to probably hold thousands of pounds of pipe, duct, conduit, and sometimes even has to be sized enough to have vibration isolation sitting on it. You've also got to go figure out, do you need embeds in the concrete? Is the slab open even big enough to take the steel? Will the support steel even fit through the opening? What loads will the support see? Can unistrut handle it, or do you need angle iron, maybe C-channel, or maybe even structural steel? And here's the bigger problem. What if the slab opening really isn't big enough? What if you need embeds cast into the concrete? What if utility weights call for bigger members than anybody's planning for? Those are questions you don't want to be asking after the concrete's already poured. My advice is, get your drafters and engineers looking at the shaft support requirements as early as possible. Even if the final design isn't done, you need to understand the concept, the loading, and the space it takes before the building even starts going vertical. Everybody coordinates the utilities. Very few people coordinate what the utilities are going to be sitting on. Mistake number 4. Nobody plans for the fire-rated enclosures. This one gets overlooked all the time. The engineer will lay out grease duct in the shaft and everything looks great in the model or on paper. The BIM model says it's fit. The shaft dimensions work. Everybody moves on, and then construction starts. The grease duct goes in and somebody realizes it still needs a 2-hour fire-rated enclosure around it. Sometimes that's fire wrap and sometimes it's a drywall shaft enclosure. And a lot of times, neither one was shown fully or accounted for in the original design. Now, that duct looks fine on paper, but it suddenly needs extra thickness, support, framing, room to install it, and inspection clearances. I've seen shafts so tight you couldn't even get your hands around the duct to install the fire wrap. The duct fit, the fire wrap didn't. And when a drywall enclosure is required, it gets even worse. Now you need framing, drywall, extra clearances, inspection access, and room for hangers and supports. The problem isn't just the enclosure itself. The problem is nobody accounted for the finished assembly. What looked fine on the plan can be impossible to build in the field. My advice? Don't coordinate the duct, coordinate the finished assembly. The inspector isn't approving the duct, he's approving the complete fire-rated system. Don't just model the duct, model the finished product, whether it's fire wrap or drywall. Mistake number 3. Nobody thinks about vibration isolation. This one catches a lot of mechanical teams off guard. The engineer lays out the piping and everything looks fine inside the shaft. The BIM model looks good, the clearances look good, everybody moves on. Then somebody starts reading the specs and realizes the piping requires vibration isolation. Now the spring hangers need space, the isolation hardware needs space, the support steel might have to be modified, and all of a sudden that shaft isn't quite as roomy as it looked during design. The pipe fit, but the vibration didn't. The problem is a lot of teams coordinate the utility itself, but they don't coordinate everything that it takes to support it. Those spring hangers take up a lot of space depending on the size of the pipe. Seismic restraints can take space, trapeze hangers can take space, support steel itself takes space, and all of it has to live right alongside the plumbing, mechanical, electrical, and fire protection sharing that shaft. I've seen shafts where the pipe technically fit, but once the vibration isolation went in, the space disappeared quick. So my advice for this one is don't stop at the drawings. Read your specs. A lot of the biggest shaft coordination problems aren't hidden in the plans. They're actually in the spec book. Mistake number 2. Nobody thinks about prefabrication. When most people look at a shaft, they assume everything has to be built in one piece at a time in the field. But that's not always true. Prefabrication doesn't have to mean building an entire shaft assembly. Sometimes it starts with something as simple as making your riser sections longer. Let's say you're in a building that's a 20-story tall structure. Would you rather install 21-foot sections of pipe or 42-foot sections of pipe? Double the length and you've just cut the number of welds or couplings or joints and inspections nearly in half. It's a huge labor savings. Could you weld a few sections together on the ground and fly up bigger assemblies into place with the crane? Absolutely. But now you've got rigging, hauling, lifting, and logistics to plan out. The point is to think about prefab early. With enough planning, a lot of shaft assemblies can be built and set as bigger modules. I've seen contractors actually build complete riser assemblies, the pipe, the duct, conduit, supports, and structural framing in a fabrication shop and ship it to the site long before the building was even ready for it. Once the assembly was built, tested, inspected, and ready to go, they lowered the whole riser into the building and tied it off at each floor with the tower crane. To somebody walking by, it looked like the shaft went in overnight. But really, there were months of fabrication, quality control, testing, inspections, and a lot of coordination happening in a controlled shop long before that assembly ever showed up on site. That's the power of prefabrication. You're pulling labor out of a crowded shaft and putting it into a controlled environment where productivity, safety, and quality are usually a lot higher. But prefab isn't free. It takes planning. Somebody's got to engineer the structural cage, design the assembly so it can be picked up by a crane. You've got to think, how am I going to haul it there? You need a rigging plan. And usually you need buy-in from the owner, the inspectors, and the GC before you can even move forward. Prefab may not make sense on every project, but it should always be on the table. Even if you're just prefabbing sections of pipes or prefabbing the supports or maybe some of the sections of the duct, every single hour you pull out of that field and put into a controlled shop buys you productivity. My advice is, at least ask the question, can this shaft be fabbed? Because if the answer is yes, you might save a lot of labor and cut the schedule risk, raise your quality, and even save a lot of money in the long run. Sometimes the fastest way to build a shaft is not build it in the shaft at all. And finally, mistake number 1. Nobody thinks about sequencing. And in my humble opinion, this is the biggest one of them all. Most people look at the shaft and ask, will everything fit? Experienced teams ask different questions. How are we actually going to build it? The challenge isn't really fitting the utilities into the shaft sometimes. The challenge is understanding how long each step takes and what depends on what. Let's say your plumbing and HVAC risers run all the way from the bottom of the building to the roof. Those systems usually have to be fully installed before you can pressure test them. Depending on the size of the project, testing a riser can take days or even a week or more. And while that's happening, other work has to wait. Same thing with grease duct. A lot of jurisdictions require grease duct risers to be light tested before they're accepted. If the shaft gets really crowded with other utilities before the testing's done, the whole thing gets a lot harder. And once the shaft gets crowded, installing fire wrap, insulation, supports, and everything else gets even tougher. I've seen grease duct that required 2 layers of fire wrap with metal banding every 12 inches. And that means the installers need enough room to physically get their hands around that ductwork to do the work. And if the shaft's too tight, what looks good on paper can be impossible to build. Sometimes the duct isn't wrapped at all. Instead, it needs a 2-hour drywall enclosure. Now you're adding framing, drywall, taping, mudding, fire caulking, and plenty of inspections. And a lot of times that enclosure has to be done before the next trade can even start their work. Same goes for insulation. Duct and piping insulation usually can't even start until the testing's complete. And if the shaft isn't protected from weather, that insulation's either going to get wet or it has to wait to be installed till later. A lot of duct sealants are specified on jobs to be low VOC water-based. That means if they get wet from rain, they wash right off, and the building's not usually dried in that early on the job. So that's why temporary roofs, weather protection, waterproofing plans, they need to get talked through early with the GC before you even start working on those shafts. This is where projects get into big trouble. One trade isn't waiting on another trade to install their work. They're waiting on them to install it, test it, inspect it, wrap it, insulate it, and then finish it. Those are very different durations. I've seen GC schedules that assume every trade's working in the shaft at the same time. In reality, a lot of shafts have to be built one trade at a time. If you don't plan the sequence right, you can end up with a shaft that can't even be built. So how do you avoid that? Well, on this project we're looking at, we actually used the BIM model and the floor plans to map out how we thought the shafts would actually get built. We figured out which utilities went in first, which systems needed to be tested, which ones needed to be insulated, and where each trade needed access through that whole installation process. But the model was really just the first step. After we built the sequence, we held pool planning sessions with the GC, the foreman, and the trade partners to nail down real durations for each step of those shafts. How long would the testing take? How long would inspections take? How long would insulation take? When could the next trade safely get into that shaft while we were still working or finishing up our work? Those pool planning sessions helped us coordinate not just how we were going to build these shafts, but how long was it actually going to take. It took a few planning sessions to get everybody on the same page, but at the end of the day, it worked. The model showed us where everything fit. The pool planning showed us how everything was actually going to get built, and it really worked well. So my advice, get the trades in the room early, walk the model, talk through the install, build the sequence, and set a realistic time frame. Everything works on paper at first. And if you don't plan early, you're bound to hit some big surprises. And those surprises can cost tens of thousands of dollars, blow up the project schedule, and make life miserable for everybody involved. But with the right planning, coordination, and sequencing, you can save a ton of time, potentially save a ton of money, and I'll do all of that before construction even begins. Remember, good planning saves time, it saves money, and it keeps projects moving forward and on schedule. Listen, if you're coming up in the trades or in MEP management, hit that like and subscribe button and follow MEP University. We'll keep bringing you real-world HVAC, plumbing, and project management lessons and hopefully help you become a better builder and a better leader.